Okay, this is week 4, lecture number 7, and on neutron diffusion. The last lecture, lecture number 6, was the first lecture on neutron diffusion. This is part of a course NE402 on intermediate nuclear engineering, which covers diffusion and transport of radiation and Monte Carlo simulation. It's a 15-week full semester course based on 45 lectures and each approximately 40 minutes. As I said before, this is my name and my personal telephone number, my personal email at yahoo.com, and official email and personal website www.nucleareng.com. Now, I'm not a very IT kind of a person, so if you send me email on nucleareng.com, I may not be able to read it. So best thing is if you send me email on my yahoo.com email address, that would be best. And of course, I would welcome feedback. So I'm going to continue this from the previous lecture where I showed you solutions in slab and spherical geometry. Now, let me do some problems to show you what kind of numbers come out of this and what kind of situations you can apply one group diffusion and two group diffusion to. So the problems given here are from one group diffusion theory, and they're useful to develop an understanding of the flux and current defined in the earlier sections of this chapter. Now, after I complete the 10 chapters that I'm going to take you through, diffusion, transport, and Monte Carlo, I'm going to apply all of this to small new nuclear reactors. And it's so I'm not going to introduce these terms again. I'm just going to apply them. So right now, just see that what could happen if we use simplistic problems. So let me take you through an example 3.1. So graphite, I told you that graphite is a very important thing for us. Beryllium, graphite, uranium, water. So these are things that you use time and again. So if you look at a graphite slab of thickness 2a in the x direction, infinite in the y and z directions, with uniformly distributed sources emitting s neutrons per cubic centimeter per second, the neutron flux I showed you is given like this. Now, when you look at this, always doubt it, to be honest, and say that no, it couldn't be right. So, so first thing, look at the boundary condition. Here, if I put a plus d instead of x, so I get same numerator denominator. It goes 1 minus 1 goes to 0. So at the extrapolated boundary, a plus d is correct. Therefore, I'm satisfied is the correct solution. Okay, so now what am I asking you? That obtain an expression for the current density in the slab and calculate the escape probability for a slab of thickness 1 mean free path. Now, this is the first time I'm probably using this term with you, mean free path. Mean free path, I told you in the first lecture, or maybe the second, that you use a macroscopic cross-section, which is n times the microscopic cross-section. So a mean free path is the inverse of the macroscopic cross-section. So it's got units of centimeter distance. So here the question is that find the current from Fick's law and calculate the escape probability. So 30% going out, 60%, how many are going out? From one mean free path. Okay. Now one mean free path, when you talk about a thickness, you don't have to say it's so many centimeters or meters thick. You can say it's one mean free path thick, it's 5 mean free paths thick. Now 10 mean free paths would be what I would call an infinite mean. So this is not infinite in the x direction, it's infinite in the y and z directions, physically infinite. So apply Fick's law, J is minus d grad phi. You know phi, so you can calculate J. Now, let's look at the escape. So how many are leaving the surface divided by how many are being produced. Now, since source is per cubic centimeter per second, so I've got to multiply this by the volume. Now it's infinite in two directions. So the volume is just in the x direction and it's of thickness 2a. So let me solve half the problem and say it's a. The thickness is a that I'm considering from 0 to a. And you can see a d over here. So actually I'm doing the problem from 0 to a plus d, the extrapolated boundary. So when you get the current divided by this, so here's the expression you get. A sine hyperbolic divided by a cosine hyperbolic. Now notice here that the boundary is at a, the physical boundary. The extrapolated boundary is at a plus d. The question was that find the escape, okay? Calculate the escape probability. So escape probability is from the physical boundary, not from the extrapolated boundary. So just to make sure that the current that you're trying to evaluate is at the physical boundary. So the total escape probability would be from the left side plus from the right side due to the symmetry of the system. So I'm just showing you half the solution. So P escape, okay, no, I'm multiplying by 2. So I'm showing you the full, so this is the full. Now, can we put some numbers in here? Now, do they both go to 0? So if they do, then use L'Hopital's rule, the derivative of the numerator divided by the derivative of the denominator. Oops, let's go up. Okay. So first of all, let's calculate the diffusion length. The diffusion length is L, and L square is, you know why we write L square? Because remember tau? Tau had units of centimeters square. So tau was for slowing down and L square is for diffusion. So the diffusion coefficient is 1 over 3 sigma transport. Now what is transport? Transport is sigma S, it's sigma T minus sigma S times mu naught bar. And if the absorption is weak, then you can write this as sigma S times 1 minus mu naught bar. So the first step, like I explained to you in lecture 1, is to find the atomic density of graphite. That's the gram density times the Avogadro's number divided by the atomic weight, atomic mass. This is, what's the units of this? Remember, I really stressed on this in the first lecture. You must know that it's grams per gram atom. So here's the density, here's Avogadro's number, here's the atomic density. Atomic density means atoms per cubic centimeter. And these really are atoms, they're not molecules, because I'm considering graphite in its atomic form, elemental form. The next step is to get the macroscopic cross sections, sigma A, absorption, scattering, and transfer. Now, absorption I picked out from Lamarche, so it's 0.0034, and I multiplied by number density. This is what I get for the macroscopic absorption cross section. This is what I get for the macroscopic scattering cross section. And this is what I get for the macroscopic transport cross section. Now do this yourself. So I've assumed that the transport cross section is sigma S times 1 minus mu naught bar. And mu naught bar is 2 over 3a to correct for the angular scattering. So we've got all three of our quantities, and we can now find the diffusion coefficient, which is just less than 1 centimeter, the diffusion area, sorry, the diffusion length, which is 58.28. Now, do you remember the age of neutrons in graphite? I showed you for water and graphite. Was it less than this? Was it bigger than this? From what I remember, it was more than twice as big as this. So this is the diffusion length. That was the, sorry, that was tau. And this is not L squared, it's L. The extrapolation distance d is 0.71 times lambda transport. So this is a correction term from transport correction term. I'll show it to you when we come to transport. For the time being, just use it. So you get a 1.9728 centimeter, which is the extrapolation distance, out of how much was the thickness of the material itself. Have we specified that? No, we haven't specified it yet. Okay, so this is the extrapolation distance. So remember we spoke of mean free path, so let's find the mean free path. So it's 1 over the macroscopic T. The macroscopic T is sigma S plus sigma A. Okay, so sigma S plus sigma A. So it's 0.38 plus this tiny number, so it's about 0.38 down here. Invert that. So 2.6 centimeters, 2.6233 centimeters is the mean free path, which means 15 centimeters infinite. So for a graphite slab of thickness 1 mean free path, in other words, this much, the escape probability again, J, calculated, so 99% of them are escaping. So there's a 99%, 99.85, so you can say it's almost 100%, they're all escaping from this graphite of 1 mean free path. Well, what else did you expect? It's only 1 mean free path. So let's look at, can we really stop neutrons from escaping from graphite? So if you repeat that calculation many, many times, so I've done this for different thicknesses, and I've shown it the escape probability. So for a tiny, tiny, tiny thickness, which we just did, almost all of them escape. But look what happens, you get about 50% escape probability from a 40 mean free path. Now 1 mean free path was about 2.2 centimeters, so 40 times this is about 81 centimeters. So at about 80 centimeters, half of them go, and about 100 times 2.2 is 220, so it's 2.2 centimeters, 2.2 meter thickness slab would let only about 22% escape. So that tells you good engineering information it gives you. Now, and why was that? It was because graphite is a weak absorber. I'm sure if you had done that for water, it would not be the case that you get such a big escape. So it's used for moderating neutrons. Now, the world's first nuclear reactor, again, uh, led by Enrico Fermi in the University of Chicago, used graphite. And it was the first critical reactor in the world. So it used graphite because lots and lots of graphite was available. So now let's say that if we were doing this for a point source in an infinite medium, uh, then this would be the thermal neutron flux, and you could repeat the same calculation. Now let's look at a really nuclear system, a multiplying system. Whenever you have uranium or plutonium in anything which you do in nuclear reactors and nuclear weapons and nuclear assemblies, then you call that a multiplying system. So multiplying meaning that it multiplies the number of neutrons by fission. So when the source is given by, now remember I told you that the source, how many neutrons get absorbed in the thermal, and K infinity. Now K, I told you, is a multiplication constant. If you want to assume an infinite system, then we use the 4-factor formula, which I did talk in good enough detail in lecture 1 or lecture 2. So you can get the source neutrons, you write the diffusion equation. Look, the minus sign is gone. There's no S over here, and we've introduced a del square phi plus K infinity minus 1 over L square, which I'm going to call the material buckling square BM square. And look what a different equation we've got. We don't have a minus sign, which means you're not going to get hyperbolic functions. You're going to get trigonometric functions, sine and cosine. So now that's the flux, a one group flux for a multiplying system. And uh, if I take the Bm square on the other side, okay, for example, if I were to write this like this and take this out, then what would you call it? You would call it an eigenvalue problem. Why? Because eigen is a German word, eigenvalue problem. Now, which means that if you have a function, if you apply an operator on it, and you get the same function multiplied by a constant, then these are called eigenfunctions for the eigenvalues. So very well known problem again, but I don't like to write it like this. So I like to write it, oops, I like to write it like, I like to write it like this. So here's the material buckling because that's how I remember it as an undergraduate. Del square phi plus b square phi is 0. Now, can you solve that system? Well, yes, of course you can, and you get sine and cosine. You apply the boundary conditions. The cosine doesn't agree with the boundary conditions. The sine, does it look good? What happens at r equal to 0? Is it finite? Is it infinite? Well, the derivative of this is cosine. The derivative of this is 1. So yes, it's finite. Okay. So now the geometrical buckling, what is it? So there's a mathematical way of looking at it because it's an eigenfunction problem, it's an eigenvalue problem, and there's a physical interpretation to it. So geometric buckling. Now, what does the word buckling mean? Buckle means to bend. So it's a geometric buckling. Something bends. So BG, the geometric buckling over here, is for a sphere, it's pi over r. But for a material, okay, I'll just show you. So for a sphere, it's pi over r, the first value of the eigenvalue. Then of course there are multiples of this. The constant a. Now, whenever you have a multiplying assembly, remember I told you it can be one of three things. It can be subcritical, it can be critical, it can be supercritical. So it all depends. Now, of course, you don't design a supercritical nuclear reactor because that could explode, and you don't design a subcritical nuclear reactor because that's not going to produce power. So you design a reactor which is critical. Now, when it's critical, then it operates at a power P, and these are related to the renewable energy coming out of every fission times the fission microscopic cross-section. This is a geometric term. When you put all these things together, then you get the constant A over here, which depends on the power of the reactor. Now, so far in table 3.1, I have only shown you the non-multiplying cases. So now let's look at the multiplying, the eigenvalue problem. Again, I'll take you through a slab and a sphere and a cylinder also. Most nuclear reactors are cylinders. No harm if you design a spherical nuclear reactor, but there aren't so many in the world which are spherical. Most of them are cylindrical reactors. And I don't know of any slab reactor. So slab reactor is just to show you that with given boundary conditions, you can solve the problem and you get a neat solution, an exact solution which says such nice things that there's a cosine distribution, there's a power, and it's a beautiful flux. You want to plot it, it's a cosine function. For a bare cubical reactor of size A, now this is a three-dimensional problem, so it's just an extension of the 1D. Look, now the flux, and I've subscripted it with T, which means thermal flux, because a nuclear reactor is a thermal. Most of the nuclear reactors are thermal reactors. They produce thermal flux. So let's say it's phi T as a function of x, y, z, and it's this three-dimensional thing, which is just an extension of the same shape of cosines in the three directions. A spherical reactor has a sine r over r kind of a flux. A cylindrical reactor, same boundary conditions, finite flux, vanishing flux at the extrapolated boundaries. And I'm going to use this in pretty serious calculations, so just look at it carefully. So there are Bessel functions that you get out of them. Some become unbounded at the inside, some become unbounded at the outside. So what remains is just J naught. Now J naught is a Bessel function, and this Bessel function, I'm just going to show you what it looks like. So, so the solution for a cylindrical reactor, infinite. Now what does an infinite cylinder mean? Well, as a student, I couldn't really conceptualize what an infinite cylinder meant. I used to think it's so huge that I can't imagine it. It actually means a cylinder of finite radius but infinite height. So, and that's the case of a spherical. Okay, now let's plot. So this exercise I'm giving you, so use the expression to find the average flux in a reactor, the neutron current, calculate and plot the quantities 4 pi r squared phi for r, small r over big R less than 0 all the way up to 1, so to the physical boundary, and describe what these quantities represent. So I'll let you do that yourself. And let's look at example 3.2. Example 3.2, consider a spherical reactor of radius this. Now, this is a very special number. Uh, it's the radius of the Godiva sphere. And let's say it operates at a power of 100 watts, which is so small, just enough for a light bulb. So consider a spherical reactor. Okay, you want to call it a reactor? No harm. So it's critical, so call it a reactor. But it's not going to power a city. So it's going to just power a little bulb. So so find the constant. So here I just want you to calculate the constant A from the expression. Such a big number. See that? Because of the recoverable energy. So, and since the buckling is pi over the, this is the extrapolated distance, so you can get an expression for phi of r. Now here I want to tell you something very important, that the flux, now this is the flux for a 100-watt reactor. So here's the radius, here's the neutron flux. It's cosine, right? So it's symmetric. Now this is the flux at 200 watt. Now can you tell me which one of these is critical? Or is none of them critical? Or are both of them critical? Well, the correct answer is that both of them are critical. So criticality does not depend on the power that you're getting out of it. It's just like driving a car at a constant speed. You can drive it at any constant speed that you want. So just like you can drive a car at a constant speed, you can drive a nuclear reactor at a constant power. So this is a small power, that's a bigger power. And look at the shape, and here you can see the meaning of the word buckling, which has more curvature, this or this. Of course, this has more curvature. Now, the first thing in nuclear engineering is to calculate the critical dimensions, criticality. Is it going to be this big or that big? So when Manhattan Project started in America, the first thing they wanted to do was to calculate that given a composition, what size is just enough to sustain a chain reaction. Now the condition for that is that the material and geometric bucklings should be equal to one another. So that's the significance of the material and geometric buckling. So you can get the K effective should be 1. So this is a non-leakage probability. So K infinity. Now I haven't shown you the fast non-leakage. I'm just showing you the thermal non-leakage. But if you want to put another term here, the 6-factor formula, then in the denominator you'd also have 1 plus B squared tau. And for large reactors, what you do is that approximate that as 1 plus B squared times LT squared plus tau, which becomes the migration area. Anyway, in this simplified calculation, we calculate K effective. The buckling of the sphere is given like this. And here is your first important estimate of critical radius. Okay, and now let's apply this. Supposing you want to design a nuclear reactor. Okay, now this is the first nuclear reactor you're going to design. And let's say that I have U235 and I have sodium. Okay. And I want to design a fast reactor, which means I want to produce power out of it. I want to produce electrical power out of my fast reactor, and I've got U235 and sodium. And the first question I'm going to ask myself is, how big is it going to be? How much U235 do I need? Now, with this knowledge that I have so far given you, just 5 or 6 lectures, uh, let's see what we can do. So in one of the examples, the core consisted of pure U235 fuel submerged in sodium coolant with mass fraction 1 to 100. First, let's calculate L square. Okay, then from the 4-factor formula, epsilon p eta f, let's calculate K infinity. Let's put these numbers here. Let's calculate the radius, critical radius, which is going to be the extrapolated radius minus the extrapolation length. So R is the physical radius. This is how big it's going to be. When we calculate it, we get this expression. Now let's put some numbers in. From the mass ratio. Now this was so important. Remember what I taught you? How do you calculate the atomic ratio? So the number density of the moderator divided by the number density of the fuel is, because the Avogadro numbers cancel out. So they're directly proportional to the gram density and inversely proportional to the atomic mass. So the ratio of number density comes out to be 1 to 1,000. So I'm going to tell you that mix 1 atom of U235 with about 1,000 atoms of sodium. So 1 spoon of this and 1,000 spoons of that. It's just like in a kitchen, you're cooking, you put some sugars and so on. Okay. So now the atomic weight of the mixture, A bar. Now go back to lecture 2 where I taught you this. So you can calculate the atomic, the weight of the mixture, which is like this. And the density of the mixture you can calculate. See how important these things are? We are getting to design a real nuclear reactor. And so we calculate the number density of the mixture. Does it look good? Does it look bad? Well, to me it looks good because there are 10 to the 24 atoms which are going to cancel out with small sigma, and my numbers look good. The number density of fuel looks small, 10 to the 19. Why is this so? Because the atomic ratio is very small, so I'm okay with it. The number density of moderator is big. I'm okay with that. There's a ratio of 1,000 between the two. I go to the tables. I get the fast cross sections because this is a fast reactor. I get sigma transport. I get absorption for fuel and moderator. I calculate the total absorption cross section for the mixture, which is the sum of absorption for the fuel and for the moderator. So I get the macroscopic cross section. So let me just calculate the diffusion length. I did that. And here it is. I tell you that this reactor is 11.3 meters dia. Is that huge? It is huge. So the volume of this spherical reactor, 11 meters, so about 35 centimeters. So 11 meters is the dia. So 11 meter is the dia. That means 35 feet. So can it fit into my drawing room? No. So I need to make it smaller. Okay, but that we'll come to next time. So the volume of the spherical reactor is also huge. With the mixture density calculated, how much material do I need? Oh my God, I need a weight of 6,000 tons, and about 100th of that, 60 tons are going to be U235. And so where am I going to get 60 tons of U235? Well, that's not possible. So I'm not going to design it like this. Okay, so this is just a one group calculation. So never mind if it's realistic or not, it's not very realistic. But it does give you numbers, but you're not going to design such a big reactor, right? Or maybe you are. But this theory tells us that yes, it is going to be critical. Now let's move on to a cylindrical reactor, infinite in height. Now the equation, a little bit tricky. This is the del square phi becomes not so simple, plus b square phi. So this equation is called, it's a special case of Bessel's equation. Bessel did this. And when you solve it, like I told you, it gives you two Bessel functions. It gives you the J naught and the Y naught. Which one do we keep? Which one do we throw? Now, look at the J naught. It's well behaved. Look at the Y naught. It's not well behaved. Because look what happens at the origin. It's going down to minus infinity. I don't want a solution which is minus infinity, so I'm going to throw the Y naught out. And I'm going to do that by putting C equal to 0. And that's going to leave me with only C. Y naught is infinite. I don't like it. So I keep a J naught. So believe me, there's mathematics and there's physical intuition. There's both. So you've got to be a scientist and an engineer, and you've got to be both. So practical sense, you must never leave because uh, you have to know what looks right and what looks wrong. So let's apply the boundary conditions. The flux at the extrapolated boundary is 0. Now, again, you get the eigenvalues Bn, and this looks a little bit better. So here's the flux. Again, if I give you a question in your assessment that find A, how would you do it? You would integrate over the flux to find the pressure, the power of the reactor. The power is the number of fissions, so if I put this sigma F in here, so sigma F times phi gives me the number of fissions per cubic centimeter per second. If I multiply that by the volume, and if it's continuous, if I integrate over the entire volume of the cylinder, and if I multiply this by ER, the recoverable energy from fission, I get what is called the power. And what kind of a power would this be, electrical or thermal? It would be the thermal power because we're talking about heat. So if you want to convert to electrical, you have to go into the thermodynamic cycle. So when I talk of power in this lecture, I talk about thermal power. So here's A, this thing over here. You can use different formula for Bessel functions, such as this one is particularly nice. The integral of J naught, if you didn't know this, it would take you a week to do it. But so these are things that you could use. And here is the neat compact expression for the flux. So for a cylindrical assembly, now that was an infinite cylinder. So a reactor is not an infinite cylinder, it's a finite cylinder. It's got a radius and a height. So if you extend that analysis, so what you see over here, you see the thermal flux as a function of radius and height. Z is the z-axis. It's got the resonance escape, the source, the volume, the sigma A, the K infinity, summation over n odd and m. Now, this is the Bessel function. See, this is the z part of it, and this is the r part. So it's separable. And these are the numbers which you get over here from these kind of expressions. And this is easy. It comes from the boundary conditions. When you set the boundary conditions, automatically you see that this is what you get. So I think I'll leave you with this over here, that I think we've made quite a little bit of progress over here. You started designing your own nuclear reactor because now you know what K effective is, you know what K infinity is, you know what L square is, you know an eigenfunction, you know eigenvalues. And here is a realistic case for K, and you want K to be 1. So you want to design a nuclear reactor that's critical, a cylindrical reactor. So far you know how to design a spherical reactor, and a cylindrical reactor. A little bit simplistic, but conceptually very, very important what we've covered today. And when we're now going to continue for the next lecture, we're going to go to more realistic two-group diffusion equation. But I think I'll stop over here and I'll leave you with exercise 3.3. Let's read 3.3. It says that plot the thermal flux in an assembly with h equal to 2r is 5 feet. Now h equal to 2r, you see, is an optimized cylinder, optimized for something. So if you have a cylinder of height and diameter 5 feet, okay, and you have a source of 10 to the 7 neutrons per second, you have, so sorry, this is not a reactor, this is an assembly. So there's a difference between a reactor and a nuclear assembly. A nuclear reactor would not have K effective less than a K infinity less than 1, because there's so much leakage going on here that this cannot sustain a nuclear fission reaction. Cannot sustain nuclear fission. So the population of neutrons is bound to decrease, and you cannot operate, you cannot produce power from it. So this is like a university experiment where you're doing some research and development. So in exercise 3.3, what I want you to do is, I want you to plot the thermal flux. And here's what it's going to look like. Now, what do you think it's going to look like? So Bessel function is nicely behaved. Cosine is nicely behaved. Where's the maximum of this? And where's the maximum? You know where the maximum of cosine is. It's at z equal to 0. But where's the maximum of the Bessel function? Well, here it is. So the Bessel function has a maximum over here at 2.405. So you're going to get where that's maximum and where the cosine is maximum, you're going to get a maximum for the flux. So that's what I want you to do. I want you to plot the thermal flux, think about it, look at it, and look at the shape, look at the buckling, look at the values, look at the value of K infinity. So again, science plus engineering, look at the values and just see what do they mean. Do I have an assembly which can go dangerous? Can it explode? Can it melt? What can happen to it? So very elementary considerations, but with real engineering consequences. Okay, so I stop over here and do practice all the solutions, especially for the finite cases. Okay, so I'm going to stop the recording. Where's the recording?